Hey guys, in this video I will present a solution to problem 4 from the first round of the German Bundeswettbewerb Mathematik 2019. We consider the decimal representation of the square root of 2, which starts with 1.4142, and we call those digits b0, b1, b2, b3, b4, and so on. Now we are given that there are k greater than or equal to 1 consecutive zeros, namely BL is equal to BL plus 1 up to BL plus k minus 1, and they are all equal to 0. And now we shall prove that L is greater than or equal to k. This tells us that if we cut off all of the digits of square root of 2 beginning with the Lth digit, then we get quite a good approximation for the square root of 2. Or in other words, the floor of square root of 2 times 10 to the power of L minus 1 is quite a good approximation for square root of 2 times 10 to the power of L minus 1. We can think of that number's decimal representation as exactly the same one as for square root of 2, but the decimal point now lies right before BL, which is why we chose this power of 10 in particular. We want to get precise bounds on the size of the difference of these two terms. First, note that of course this floor is less than or equal to that term, and furthermore, because the square root of 2 is irrational, we know that there must be a strict inequality between those two, and therefore we can know that this difference is indeed greater than 0. Let's take a look at the decimal representation of this term. Due to the definition of the floor function, it is less than 1, and so all of the decimal digits before the decimal point are equal to 0. Furthermore, this is an integer, and so all of the decimal digits after the decimal point are equal to those of square root of 2 times 10 to the L minus 1. And we have already noted that they start at BL and then BL plus 1 and so on. But those are all equal to 0 up to BL plus k minus 1. And so this difference is strictly less than the number beginning with k minus 1 zeros after the decimal point and then having a 1. And that is precisely equal to 10 to the minus k. And so we can bound this from above by 10 to the minus k. At this point, I will show you a really cool trick with which we are going to solve the problem. In the end of this video and in our solution PDF, we have a more advanced exercise where you can try to apply this trick. The idea is that the square root of 2 squared is again an integer. And therefore, if we find a polynomial where this is a factor of that polynomial, and if we multiply all of the terms out, this only appears in even powers, then we're going to obtain integer values for this polynomial, which will help us get a lower bound. In this concrete case, we are considering the quantity square root of 2 times 10 to the power of L minus 1 minus its floor times the square root of 2 times 10 to the power of L minus 1 plus its floor. This is equal to the square of square root 2 times 10 to the power of L minus 1, so 2 times 10 to the power of 2L minus 2, minus the square of its floor. So in total we get an integer. To make use of this fact, let's notice that both these factors are positive, and therefore this is indeed a positive integer, and so we can bound it from below by 1. Dividing by this second factor, we will actually obtain a lower bound for the term we are actually interested in, namely the square root of 2 times 10 to the power of L minus 1 minus its floor. This is greater than or equal to 1 divided by square root of 2 times 10 to the power of L minus 1 plus the floor of square root of 2 times 10 to the power of L minus 1. Using the fact that this floor is indeed less than square root 2 times 10 to the power of L minus 1, all of this is greater than 1 divided by square root 2 plus square root 2 times 10 to the power of L minus 1, or in other words, we get that all of this is greater than 1 divided by 2 times square root 2 times 10 to the negative L plus 1. Of course, 2 times the square root of 2 is less than 10, And so this is actually bounded from below by 10 to the power of negative L. This finishes our proof, because if we remember that this term is actually bound from above by 10 to the power of negative k, we can conclude from this that k is less than L, which is even stronger than what we wanted to show. As announced, here's a related problem to this one, and you can try to solve it on your own and leave your ideas in the comments if you want to. Let epsilon greater than 0 now show that there are integers a, b and c not all equal to 0, satisfying the absolute value of a square root 2 plus b square root 3 plus c square root 5 is less than epsilon. Moreover, we want to prove that for such ABC, we have that their maximum absolute value is greater than epsilon to the power of negative 3 divided by square root 30.